All right, so today we get into the final part of investigation 3.4. So it says, how can we use similar triangles to find the distance that is difficult to measure directly? So we got a couple examples here. So new vocabulary word, we're talking about nested triangles. That says triangles that share a common angle are sometimes called nested. In the figure below, triangle ABC is nested with triangle ADE. And again, share a common angle, which means they share this angle right here, right? A, right? B and D are a little different. They're not the same angle, right? C and E. But A is the same angle, and that's what we're talking about when we use the word nested. Okay? So, taking that into account, so here's our problem, our first problem that we're going to deal with today. So, it says, Darrell, Angie, and Tanya are designing a triangular boardwalk that crosses a river for a class project. They make several measurements and sketch the diagram below. So you can see the big picture right there. So what I want you guys to work on this very first part with your teammates is parts A and B. So it says the triangles in the diagram above are similar. Okay. So what is the scale factor from the smaller triangle to the larger? So from the smaller one to the larger one. So we're going bigger, right? All right. What is the distance across the river from stake 1 to tree 1? So where's stake 1 at? Right? And tree 1 is up there, right? So basically, they want to know what this distance is right there. Okay? And then describe the relationship between the perimeter of the smaller triangle and the perimeter of the larger triangle. Again, we've had a lot of experience doing this over the previous 2 investigations, right? All right, so again, with your teammates, we'll give you guys about 10 minutes to work on that. Okay? All right, go for it. We're going to pause the video. Here. So, what was the scale factor? Well, if we look at this, we got 2 triangles here. You got this one, right? And then you got this one. So what information can we use to help us find the scale factor? Aiden. Right. So if you take 140 and divide it by 80, right? What'd you get? One what? 1.75. So that's our scale factor. Because remember, to go from the little triangle to the big one, you have to go. It has to be a number bigger than 1, right? So if we're scaling up, it's got to be bigger than 1. If we're scaling down, it's got to be smaller than 1. Good. All right, so that little distance right here that we were looking for. Okay. So we never really got the whole distance, right? We got this one, right? 120 to the small triangle. So the big one, how did you figure that out? Well, remember, if the small triangle's length from here to here is 120, isn't this a similar side? So we can use the scale factor, right? You would take 120 and multiply it by 1.75. Right? What would that give you? Joey? 210. But remember, that 210 is the whole distance. We only want this part. So what do we have to do to that 210? Not divide by 2. Joey? Subtract the 120, which they already gave us this distance, right? So if I take 210 and subtract 120, what do I get? Joey? 90 feet. So that's the distance from the tree 1 to stake 1. So again, what do we know about the perimeter then? for part B. Describe the relate. If the scale factor is 1.75, what do we know about the perimeter? Come on, we should know this one out of the back of our hands. So only a few people want to talk today. Same people keep raising their hands. What do we know about the perimeter? Compared to the smaller triangle, the perimeter of the larger triangle should be how many times bigger? 1.75 times bigger. So the perimeter of the larger triangle is 1.75 times bigger than the perimeter of the smaller triangle. All right. So on the back now, we got a different little scenario. So it says another group of students sketches a different diagram with similar triangles. It's not as long going this way, right? So they put their stakes at different places. So there's a sketch. So now, I'll give you guys a few minutes to work on this one. What's the scale factor of going from the smaller triangle to the big one? And then it says, does the second group get the same measurement for the width of the river from stake 1 to tree 1? Okay. So you guys are going to work on that right now for, again, about 10 minutes. Just before the big hands on the 11, we'll come back together. No, if we go the other way, it's a smaller number. From larger to smaller, it's going to be less. All right, so let's see what you guys can figure out here. Okay. A little bit different. All right, let's bring it back in. So what'd you come up with a scale factor? I don't know. 4. How'd you come up with that?
I took 140 feet and then I divided it by 35 feet.
Right, there's your same sides, right? So if you do 140 divided by 35, you get 4. So scale factor is 4. Because remember, you got the small triangle here, and then the big triangle there. All right, so it says the second group get the same measurement from stake 1 to stake 2. Well, if the small one is 30, right, what do we have to multiply 32 to find the total length here? Joey. 4, right? So 30 times 4 is what? 120. So 120 is this whole length. But again, we only need to go to stake 1, so what do we got to subtract out? Joey? 30. So 120 minus 30 gives you, was that the same? Sure is. So that's the same exact width from tree 1 to stake 1. Okay? So you see how we can use the scale factors of similar figures to solve real life problems. So under your summary, you're talking 120 feet. That's a long tape measure, right? So again, we can use that to measure distances that are difficult to measure. And then, of course, nested triangles. That's when they share that angle, right? And just remember, if we're scaling up, right, meaning that we're going from a smaller triangle to a bigger triangle, that scale factor has to be greater than 1, right? If we're scaling down, that means we're going from a bigger triangle to a smaller triangle. That scale factor has to be a number less than 1, okay? That's important. All right.